We see them everywhere, but have you ever really thought about the pipes running under our cities or through these massive industrial plants? They just look like simple hollow tubes. But the truth is, they're total unsung heroes of engineering. They're meticulously designed to handle incredible stress for decades on end. Today, we're going to pull back the curtain on all that hidden complexity. So that brings us to the big question for this explainer. How in the world do you take a simple tube of metal and guarantee, it can survive decades of extreme heat and pressure without, failing catastrophically? Well, the answer is this fascinating mix of physics, material science, and a very healthy dose of caution. All right, let's get into it. Okay, so before you can do a single bit of math, you have to lay the groundwork. This is what we call the blueprint phase. It's where you make these fundamental choices that are going to dictate literally everything else that follows. First things first, everybody on the project needs to be speaking the same language. And in the world of piping, that means picking a sizing standard. You've basically got two camps: NPS, or nominal pipe size, which is the inch-based system you'll see a lot in North America. And then there's DN, or diameter nominal, the metric system that's used pretty much everywhere else. It's kind of like inches versus centimeters, just different ways to measure the same thing. So a 2-inch pipe, for example, is called a DN50. Simple as that. Now, a pipe isn't just made of some generic steel. Oh no. It's a very specific recipe, a carefully chosen alloy that's built for a very particular job. You have to ask, what's it going to be carrying? Is it something super hot? Then you're probably going to use a high-temp carbon steel, like A106. Is the fluid corrosive? Is it going to rust things out? Then you need something tough like A312 stainless steel to fight it off. The material has to match the mission. And it's not just the pipe. All of its buddies, the flanges, the valves, everything connected to it, they all have to be rated for the pressure. The easiest way to think about these pressure classes is like weight classes in boxing. A class 150 fitting, that's your lightweight for lower pressure stuff. But a class 1500, that is your heavyweight champion, built to handle immense force. And the key is, everything in the system has to be in the same weight class to work. All right, with our basic choices made, it is time for the main event, the math. This is where engineers prove, on paper, that the pipe they've designed is actually strong enough to do its job safely. The first key number we need is the design pressure, what we call P. Now, this isn't just the normal everyday operating pressure. Nope. This is the absolute maximum pressure the system could ever experience, even in a worst-case scenario. It's that constant, relentless outward force that the pipe wall is fighting against every single second of its life. The other side of that fight is the allowable stress, or S. I love this term. Think of it as the material's strength budget. Based on that specific steel we chose earlier, the engineering codes tell us exactly how much stress it can safely handle, day in and day out, without even breaking a sweat. It's the pipe wall's inherent ability to push back against that pressure. And this is where it all comes together in one super critical formula. Now, don't worry about memorizing the letters or anything. The big idea here is that this equation works like a balancing scale. On one side, you have the pressure pushing out. On the other, you have the material's strength budget pushing in. The formula balances those two forces to calculate T, the absolute minimum wall thickness you need to keep everything safe and sound. So let's say we run the numbers for a pretty standard pipe. The formula does its thing and spits out a result, 7.06 millimeters. That number is the magic number. It's the absolute thinnest the pipe wall can be, according to the laws of physics. If it gets any thinner than that, we are in the danger zone. But here's the thing. Do we go out and order a pipe that's exactly 7.06 millimeters thick? No way. Absolutely not. In engineering, just enough is never good enough. You always build in a safety buffer. So we look at the standard pipe sizes that you can actually buy, and we pick the next one up. In this case, that would be a standard Schedule 40 pipe, which has an 8.0 millimeter wall. That extra millimeter might not sound like much, but that is our margin of safety. It's our peace of mind, and it is completely non-negotiable. Okay, so the design is done, the math is solid. But a brilliant design is totally useless if you can't clearly tell the people who are actually going to build the thing what to do. And that brings us to the engineer's shopping list. The answer is this thing called an isometric drawing. This is not just a simple sketch, okay? It is a detailed 3D map for the construction crew. It has to show absolutely everything. The exact route the pipe takes, every single elbow and T, where every weld needs to go, and even where the supports that hold the whole thing up are located. It's the master blueprint. And that drawing comes with a partner, The Bill of Materials, or BOM for short. If the drawing is the map, the BOM is the project's ultimate shopping list. It lists every single component, right down to the last nut, bolt, and gasket, with its exact specs and how many you need. It ensures you have all the right ingredients before you start cooking.
So, the pipe is designed perfectly, it's built perfectly. Job done, right? Haha, not even close. Now the pipe's lifelong battle against the real world begins. And guess what? Engineers have to plan for that too.
This is the question that keeps plant operators up at night. We did everything right on paper, but now this thing has to operate in a harsh environment for the next 20, maybe 30 years. What could possibly go wrong?
Well, as it turns out, quite a bit. Engineers think of these as the 5 main enemies of a pipe. First, you've got corrosion, which is basically rust trying to eat the pipe from the inside out or the outside in. Then there's erosion, which is like a constant sandblasting effect, wearing away metal, especially at elbows. Gaskets can fail over time, causing leaks. The pipe itself will expand and contract with temperature changes, creating thermal expansion stress. And finally, vibration from nearby pumps or machinery can literally shake it apart over time. So how do you fight these enemies? With a really smart, proactive maintenance plan. It starts simple, with things like weekly visual walkarounds, just to look for trouble. Then you have regular checks, like making sure supports are tight. The really critical stuff includes yearly ultrasonic tests, or UT, where they measure the wall thickness to see if it's getting thinner. And every few years, you do a big one, a full inspection, like a hydro test, to confirm the whole system's integrity. Okay, we've covered a ton of theory. So now, let's see how this all snaps together in a super quick case study of a real high-pressure industrial gas line. All right, check out our new inputs. We're dealing with a 6-inch line, but look at that pressure, 32 bar. That is a huge jump from our first example. The temperature's way up too. And notice this last line, corrosion allowance. For this critical pipe, the engineers have literally built in 3 extra millimeters of steel that they expect to rust away over the pipe's life. It's sacrificial thickness. So you take these much tougher conditions, you plug them back into our formula, and what do you get? A new minimum required thickness of 9.55 millimeters. That's a whole lot thicker than before, and it's a direct result of that higher pressure and temperature. The math doesn't lie. And what do they actually choose for the final pipe? They jump all the way up to a much thicker Schedule 80 pipe with a wall that's almost 11 millimeters thick. Why? Because for a critical service, like a high-pressure gas line, the safety margin has to be even bigger. You simply do not take chances with this stuff. And here it is, the final plan. You can see its unique ID number, which tells an engineer everything about its size, what it's carrying, and its pressure class. You see the key parts it needs, how often it needs to be supported, and a very, very strict inspection schedule. This is the pipe's entire life story, all on one page, from concept to long-term care. So, the next time you see a simple pipe, I hope you remember that it is anything but. Inside that simple shape is a complex story of careful choices, critical calculations, and a deep, deep commitment to safety. It's just one small piece of this incredible hidden network all around us, engineered to perfection.